Both the curl and the divergence are essentially types of derivatives for vector fields. And they satisfy a number of nice properties, just like the standard derivative in single variable calculus does. And in fact, we can think of these properties as flowing from properties of that basic derivative. So in this case, we want to prove a general statement about, prove a general property about the divergence of a product of a scalar function, little f, which is a function from R3 to R, and a vector field in R3, G. And it's essentially the product rule for divergence. So the divergence of the product f times g is f times the divergence of g plus the gradient of f times g, where times here, I mean the dot product of these two vector fields. The gradient of f is a vector field and g is a vector field. And so if I take their dot product, I get a scalar function. Again, the divergence is a scalar function, so times f is a scalar function. And so that makes sense. We're saying the scalar function on the left is equal to the sum of these scalar functions on the right-hand side. All right. So how do we go about proving a statement like this? Well, we want to do it in general. So basically what we need is some general form for the vector field G so that we can actually get into computing the divergence, because we know how to compute divergence if we have, for instance, the components of a vector field. So let's get a little bit more specific about G. So suppose it has components P, Q, and R. So all of P, Q, and R are really functions from R3 to R. They're scalar functions. Now that implies that f times g, well, it's a scalar times a vector. So I multiply that scalar in every component. So I have the product of f and p, the product of f and q, and the product of f and r as functions. Okay, so we haven't gotten any less general, but we've gotten to some specifics as far as we've given names for the components of G. So now we can take the divergence of this vector field fg in the way we would take the divergence of any specific vector field. So I'm going to take the partial with respect to x of the function fp and add it to the partial of with respect to y of fq, and then add the partial with respect to z of f times r. Okay, so whatever f and p, q, and r, whatever functions those happen to be, the divergence of f times g is going to be this function. And now, of course, in each one of these single variable derivatives, these partial derivatives, I have a product rule. So this is f times the partial with respect to x of p plus the partial with respect to f times p. And then I can apply the product rule for the next two functions as well. So I have f times the partial with respect to y of q plus the partial with respect to y of f times q, and then f times the partial with respect to z of r plus the partial with respect to z of f times r. All right, so there you go. So this is what we have. And now at this point, we want to essentially try to clean this up and make it look like the right-hand side of the equation. So we started off with the left-hand side, and we just want to show through a string of equalities that we get the right-hand side. So the first term here is f times the divergence of g. So it's the only thing with f times something. So basically we should just look at all the terms here that have a factor f and factor out that f and see what we get. And we get the partial with respect to x of p plus the partial with respect to y of q plus the partial with respect to z of r. All right, so that's what these three terms contribute. And then these last three terms that are left over, we can recognize, right? So we have the partial with respect to x of f times p plus the partial of y with respect to f times q plus the partial of z with respect to f times r. So p, q, and r are the components of g, and fx, y, and fz are the components of the gradient of f. So I'll rewrite these just to emphasize that we're grouping them together. So plus partial with respect to z of f times r. And then so here we have, this is essentially the gradient of f dot product with g, because the gradient of f has components this, and g has components p, q, and r. On the other hand, this is f times, and then this is of course exactly the divergence of g. And so there we have it. So we started with the divergence of f times g, and we ended up with f times the divergence of g plus the gradient of f dot g. So we've completed our proof. Some people like to draw a box. Some people say QED, as Euclid did. But in any event, we've demonstrated what we set out to demonstrate, that this property of the divergence holds in general. And just to review, we did this not by getting into a specific vector field or function, but by getting a little bit more specific about what G is, in this case writing out its components. And once we wrote out the components of G, then we could get a lot more specific about what the divergence should be and compare it to this right-hand side.